Greetings. Today we are going to solve for the heat of solution. Remember that a solution is a homogeneous mixture in which it has ions floating around or molecules floating around, and it looks like one thing, even though that it has more than just water in it. So in addition to that, we're going to be able to solve for the delta H of solution. So you may see my formula down here in which we are going to dissolve ammonium nitrate, and it's going to break apart into its constituent ions. We have the cation, which is the ammonium, and then we have the anion, which is the nitrates, and the AQ, remember, means that it's dissolved in water. It started out as a molecule in the solid phase and broke apart into its subsequent ions, and it is now floating around. And typically we would have this delta H with a positive numerical value to tell us how much heat and in what direction, exothermic or endothermic, but we don't have it here. We have everything else, and that's what we're going to solve for today. So we're going to learn how to solve for the delta H of a solution. So here's the question. We're going to add 3.88 grams of solid ammonium nitrate, so just chemicals, and let it dissolve in 60 grams of water. We're going to put it in a coffee cup calorimeter, which essentially is just a styrofoam cup with a thermometer down the center, maybe a stir rod, and we're going to mix the chemicals together. And we noticed through this example that the temperature has dropped. It's dropped significantly. Remember, water has a high heat capacity. So in order for it to drop this many degrees means that there was a lot of heat exchange. So now we're going to calculate the delta H, and we're going to assume that the specific heat is the same as that of water. All right, so using our MCAT formula, we are going to solve for the heat of the liquid first. So we have the mass of the solution. So remember that we have the chemicals plus the water is going to equal the solution. So we had 60 grams of water, 3.88 grams of chemicals. Let's add those together. Equals 63.88. And we are going to assume that the specific heat capacity of the water is going to dominate the overall average between the chemicals specific heat capacities and that of water. So we're going to round in favor of the water. So we're going to use 4.184 joules grams Celsius. Oh, remember that's grams. And then the final temperature minus the initial, we actually had a drop. And having said that, we should get a negative number for our temperature range. So our final heat is negative 1229.5 joules. Okay, here's the tricky part. Our thermometer is measuring the water, not the chemicals. So we have to do a little bit of flip-flop in here. So we know that the heat of the reaction and the heat of the liquid equal each other because we have a little coffee cup calorimeter, and inside that is our little universe, and no heat's going to come in or out of our little environment. So all the heat from the system is going to be transferred to that of the surroundings or vice versa. So remember that the temperature dropped from the surroundings, the liquid, okay? So if the temperature dropped, that means that it was giving its heat away. And what was it, the heat was being drawn in by the reaction. So remember that the reaction is endothermic. However, the heat being pulled from the surroundings is I guess the heat is coming from the surroundings to the inside the system, and think of this like a cold pack, and that's exactly what it is. These are the exact same chemicals that are inside a trainer's cold pack. They crunch it up, they're breaking up the liquid with the solid, they're mixing it around, and the temperature drops. Well, the heat is being pulled from the surroundings and going into the chemical reaction, and that's exactly what we see because our thermometer lives in the liquid or the surroundings. So that being said, our reaction, if we substitute some numbers in here, 1229.5, we're going to get positive 122. Oops, too many twos. 1229.5 joules. All right, so we had to flip-flop some signs just to represent that now we're discussing the reaction. The reaction is endothermic. It's pulling heat away from the water. And remember that we're almost there because our delta H wants it in kilojoules per mole. So we have joules. Let's do a quick conversion. If we convert this to kilojoules, we're just moving the decimal place over 3 spots to the left. Therefore, we have 1.2295 on the top. Now let's solve for the denominator. So how much starting chemicals do we have? Well, we had 3.88 grams of NH4, NO3, a little bit of stoic. For every 1 mole, it's 80.05 on the periodic table. Now we're going to quickly divide these two because they're on the same side of the equal sign, and we're going to go diagonally. So we're going to go top to bottom, and we should get how many moles? 0.048 moles. Let's put that in the bottom, 0.048 moles. So our delta H, get your calculator out, should be 1.2295 divided by 0.048. Therefore, it should be 25.61 kilojoules per mole. And that is that in regards to our delta H equals, what was it, 25.61. 25.61 kilojoules per mole. And that's how you solve delta H when it's not provided for you in terms of the thermochemical equation.